2.4 Continuity. Here's a little comic because we are going to be talking today about one-sided limits, so this is a little left-handed limit. Let's start off with the definition of continuous. In order for a function to be continuous at a point A, it must satisfy three conditions. The first one is that f of x has a limit as x approaches a. The second one is that f of a is actually defined, and the third one is that the limit is actually equal to f of a. So what do I mean by this? In this drawing here, you can see our function is continuous because the limit from the left equals the limit from the right, and it also equals the function value at that point. So those are the three things that we need for continuity. I also like to think about a continuous function as one that we can draw without lifting up our pencil. See, when we're drawing this function here, we can draw the whole thing without having to lift our pencil. If, for instance, we had a different function, say it looked like this and it had a hole right here, well, we can't draw this function without lifting up our pencil at the hole. And then right here it says, in words, a function is continuous if a small change in x produces only a small change in f of x. And that's just because, as I move along, it should just flow. There shouldn't be any big jumps or anything like that.
So let's look at an example. Let's discuss the discontinuities here. Well, we can obviously see that it's discontinuous right here at x equals 1. Where else? At x equals 3, we see a problem. And then here at x equals 5. While we're on this example, why don't we quickly talk about where f is defined, just so we don't get these two things mixed up. Well, our only potential problems are where it was discontinuous, right? So is f defined at x equals 1? No, right? No, the function has no value at x equals 1. What about at x equals 3? Yeah. Because right here, that is at x equals 3, that's what the function equals. And what about at x equals 5? Yeah. It's this point right here. This is f of 5.
Okay, now let's look at a couple of examples. We're going to start by doing them algebraically, and then we'll look at them graphically. To look at A here, let's start with thinking about where is our problem spot. Well, our problem spot would be where the denominator equals 0, because thou shalt not divide by 0, right? So x equals 2 is going to be our problem spot. This function right here is not defined at x equals 2, so it must be discontinuous at x equals 2. In order to do B, we need to know what the function 1 over x squared looks like, first of all. And we actually need to know what this looks like without using our calculator. I'm stressing that because on the AP exam, half of your exam will be taken without using your calculator at all. All right, now that you've done that little exercise, and assuming you know what 1 over x squared looks like, you know that the limit as x approaches 0 of 1 over x squared does not exist, right? Because it goes off to infinity at x values near 0. So, since the limit does not exist, we clearly know that we have a discontinuity at x equals 0 because the limit didn't even exist there. In order to do part C, let's go ahead and break this down into the three things we need. We need to know the limit and we need to know the function value at that point. But in order to know the limit, we need to know the limit, and we're looking at 2 here, right? So the limit as x approaches 2 from the left. Let's then look at the limit as x approaches 2 from the right. And finally, the third thing was the function value at that point. So we'll just look at f of 2. Okay, so let's go ahead and evaluate these three things. In order to do the limit as x approaches 2 from the left, we would use this top function here, right? Because this function is only at x equals 2 exactly. So from the left and the right, we're going to use this function for both of them, actually. So we'll do the limit as x approaches 2 from the left, and we use that top function. And so now I'm going to try and factor. So I have an x, I have an x, I have a 2 and a 1, and I need a negative and a positive. Great, those cross out. So now the limit as x approaches 2 from the left of x plus 1 is just 2 plus 1, or 3. Great. And then the limit as x approaches 2 from the right, I use that same function, right? And so I know my answer there is just 3. But what is f of 2? F of 2, I use this function. F of 2 is 1. Therefore, since the limit as x approaches 2 of f of x does not equal f of 2, our function is discontinuous at x equals 2. If we look at this graphically, we can see in part A, we said it was discontinuous at x equals 2 because there was a hole there. In part B, we said that it was discontinuous at 0. The limit does not exist there. It's going off to infinity. And then in part C, again, we have this hole, but the function value is defined at a different point. So it is discontinuous there at x equals 2. To quickly review the different types of discontinuity we have removable discontinuities. So that is like what we saw in both figures A and in figure C here. Those are removable discontinuities. They have holes in their graphs, and they're actually removable discontinuities because I can remove the discontinuity by redefining this thing as a piecewise function and filling in that hole. So what do I mean by that? Remember in part C, we had this function here, but defined as a piecewise. So we had f of x equals x squared minus x minus 2 over x minus 2 for all values except for 2. And then at x equals 2, we had it defined as 1. But what if we found here that the limit from the left and the limit from the right was 3? So this point was 1, 2, 3. So we had that point, 2, 3. What if we made this function value here 3? Then we could kind of fill in that hole there, and we would have redefined this function as a piecewise function that was continuous. We're going to talk about that more later, but that's how I think of it as a removable discontinuity. It's one that has a hole, because if I filled in that hole, it would be continuous. Then we have infinite discontinuities, so that's just this one in part B. It's going off to infinity at x equals 0. And then we also have jump discontinuities, which we didn't do here today, but those are step functions. For an example, you can see that it jumps at integer values. We have discontinuities. So at 0, at 1, at 2, at 3, we have discontinuities, and it jumps there. We can also talk about one-sided continuity. So a function f is continuous from the right at a number a if the limit from the right equals the function value at that point. And a function can also be continuous from the left. So you can see in this function right here, we have continuity from the right because the limit as x approaches 0 from the right equals 0, and f of 0 also equals 0. Another example, let's just look at x equals 2 for a moment. What do we have there? We have the limit as x approaches 2 from the right is equal to 2, right? And what is f of 2? F of 2 is 2. And so we have that it's continuous from the right because the limit as x approaches 2 from the left, what is the limit as x approaches 2 from the left-hand side? That's 1. So it's not continuous at x equals 2, but it is continuous from the right only.
We can also have continuity on an interval. So let's look at this example here, and let's try and show that the function is continuous on the interval from -1 to 1. So if the domain of our function is, that would be a good starting place. Well, we know that what's underneath the root cannot be negative. So we know that the 1 minus x squared has to be greater than or equal to 0. In other words, let's bring the x squared to that side. And I like to have the x squared on my left, so I'm going to write it like this. And so if I take the square root, remember that I'll take the square root of this, but I have to keep in mind that it can be between -1 and 1. Don't forget that when you divide by a negative, your signs switch. All right, and so we just learned that the function is continuous on its domain. Therefore, f of x is continuous on -1, 1 inclusive. Now, let's learn some laws of combining continuous functions. And if f and g are continuous at a and c is a constant, then we know that f plus g is also continuous, f minus g is also continuous, c times the function is continuous, f times g is continuous, and f divided by g is continuous so long as g of a does not equal 0. Here's a theorem, polynomial and rational functions. Any polynomial is continuous everywhere. That is, it is continuous on all real numbers. And any rational is continuous wherever it is defined. That is, it is continuous on our domain. And again, we're going to look mainly there that the denominator does not equal 0. So let's take a look at an example. All right, what do we know here? Well, let's first take a look at the domain because we know it's continuous everywhere on its domain. So let's make sure that we're not interfering with that. What is the domain? Well, the domain is all real numbers except for what? We can't let this equal, the denominator equals 0. In other words, 3x cannot equal 5, x cannot equal 5/3, and we're not looking there, so let's go ahead and just evaluate. We can just substitute it in since -2 is on the domain. Stick in a -2 and we get 6, and that's -1/11. All right, so you can just apply direct substitution because -2 is in the domain. Easy enough. Types of continuous functions. So here are some that you should just know they are continuous. So let's use that to evaluate this limit here. You know sine of x and 2 plus cosine of x are both continuous on all real numbers, right? Because the last theorem just said that trigonometric functions are continuous everywhere. And we know that 2 plus cosine of x can never equal 0. You can just apply direct substitution since it's continuous. And so we have the sine of pi over 2 plus cosine pi. Now you gotta know what the sign of pi is. Remember our unit circle here. Here's 0, here's pi over 2, here's pi, here's 3 pi over 2. Our coordinates right here are -1, 0, meaning that the cosine of pi is -1 and the sine of pi is 0. So we have 0 over 2 minus 1, which is 0 over 1, which is just 0. So that's it. That's all we have to do. We can just apply direct substitution since the function is continuous at x equals pi. The really important part is right here. So let's take a look at an example because here's just a lot of words that look really, really confusing. So by saying that we can apply it in any order when we have a composition of functions, what I'm saying is I can go ahead and, since I'm doing this arc sine of this function, I can apply it in the other order. So go ahead and just say, well, let's apply the limit first. Let's just concentrate on this limit. How am I going to evaluate that? Well, when I don't know what to do, remember, I just try and multiply by the conjugate. So let's try and do that. Let's try and get rid of the radical on the top and just see if that brings us anywhere. You know, sometimes we just have to try things and hope that they work. Remember I said never multiply these things out because hopefully something's going to cancel out. And lucky for us it does. Until I ensure that my denominator doesn't equal 0, and it doesn't, so I can just apply direct substitution here. And so I have 1 over 1 plus 1. And remember, the arc sine of 1/2 is saying what is the angle whose sine is 1/2. So I like to just remember my 30, 60, 90 triangles. And if this is 1, this is 1/2, and this is √3 over 2, you need to know that. So what is the angle whose sine is 1/2? That corresponds to 30 degrees, and in this class we're just going to talk in radians. So 30 degrees is pi over 6. So that's our answer. Finally, the intermediate value theorem. This is another one of those theorems that looks confusing, and it's rather obvious when you really think about it. And this is going to be a really important one in this course. What we're saying here, suppose that f is continuous on the closed interval a,b, so it's continuous, and let n be any number between f of a and f of b. So here we have f of a, for example, and here we have f of b. And we have this n, which is a number between the two. Then there exists a number in the open interval, okay, this is open interval, such that f of c equals n. So just saying that there has to be some number in the middle. It can happen once, or it can happen more than once that it equals that number. Again, let's look at an example that doesn't really make that much sense. This is the context we usually see the intermediate value theorem in. Show that there's a root of the equation. Pretty much, in order for it to be a root, we have to say that it equals 0 somewhere. Okay, so if we were to evaluate the endpoints, f of 1 and f of 2, and if one of them was positive and the other one was negative, then we would know that it had to be 0 by the intermediate value theorem. So let's go ahead and try that. F of 1 is going to be 4 minus 6 plus 3 minus 2, which equals -1. And f of 2 is going to be 4 times 8 is 32 minus 24 plus 6 minus 2, which is 12. And look at this. This is less than 0, and this is greater than 0. Therefore, by the intermediate value theorem, we have to write by the intermediate value theorem, there exists a number C. There's some number on the closed interval 1, 2, right? I'm sorry, the open interval 1, 2, such that, you can just abbreviate that ST if you want, that's good mathematical notation, such that f of C is equal to 0. So what am I saying? I'm saying, well, basically, and I'm not going to draw an accurate function here at all, but I'm saying since f of 1 is negative, it's below, and f of 2 is positive, well then there must be some value that in between 1 and 2, there must be some value between 1 and 2, okay, that's what that's saying, that hits the axis. And that's all I'm saying with the intermediate value theorem. Okay, and then the next slide, we just see the actual graph there.
That's it for this lesson.